So in addition to gathering chemical information about our celestial objects or our cosmic messengers, when we gather light information, or more broadly speaking, electromagnetic radiation from those objects, we can understand their temperature or infer their temperature. For example, if we have this poker and you're going to heat this poker up over time, it's going to start out as not glowing, then it's going to glow orange, maybe glow red, and then maybe glow white hot. So just by looking at this poker, you don't have to touch it to understand what the temperature is. Our eyes are gathering information, we're translating it to a temperature. Kind of along those lines, we don't have to visit the stars. We can actually kind of map out the radiation they're sending us and infer what temperature they are. So just like that poker, when it first started out, when it was cool, it wasn't oozing any, it wasn't glowing. But after we heated it up, it began to glow so we could see it. And actually, all objects, unless they're at absolute zero, okay, temperature-wise, all objects kind of ooze out a certain amount of radiation. And we can go ahead and we can make a radiation curve, an electromagnetic radiation curve, out of what an object is oozing. For example, there are 4, count them, 1, there's a black one here, red, yellow, and blue. There are 4 objects, and this is the radiation curve of those objects. Now notice what we have plotted here along the y-axis, along the x-axis, we have wavelength. Shortest wavelength, as we've been doing over here on the left. Of course, that would be our highest energy. Longest wavelength over here on the right. And then along the y-axis, we have intensity. So, what are those curves? Well, let's take a look. The blue curve. Now, notice that the blue curve is skewed over here. Actually, there's this sweet spot we call its lambda max. Let me see. Right here, can you see where it peaks out at a pretty darn high wavelength? High energy, short wavelength. Okay, so this actually is shorter wavelength than visible light. And as it turns out, this is the hottest star. The temperature in units of Kelvin are 15,000 Kelvin. The yellow radiation curve represents the distribution of energies we receive from our sun. The surface temperature of the sun is about 5,800 Kelvin, 5,800 Kelvin units. So can you see where our sun, 5,800 Kelvin, is cooler than the 15,000 Kelvin star, another star? Okay, its lambda max, by the way, would be about here. Then we move on to an even cooler star, a star that is only 3,000 Kelvin. And can you see where, as we're getting cooler and cooler objects, the lambda max, the maximum wavelength that they peak out at, shifts over to longer and longer wavelengths. So the last object up here is a human being. In general, on the Kelvin scale, we run about 310 Kelvin units. So this is our signature, our radiation signature. Isn't that cute? So there are 2 kind of laws of thermal radiation, and they make sense. They're kind of consistent with what we've been talking about. For instance, the hotter an object is, the more light at all frequencies it will ooze out. So for instance, of these 4 objects, a hot star, the sun, a cooler star, and humans, can you see that intensity-wise, the hottest star wins out? Okay. The other thing is that hotter objects will have a higher average temperature. So we said that with regard to wavelengths down here, this is the shortest wavelength listed here, so this would have high energy. Okay, longest wavelength, low energy. Low energy. And so this is, remember I kind of wrote in the sweet spots, you know, that's kind of what I was trying to say there, that the hotter the object, that will be this blue star, it will have a higher average temperature. Let's take a look at another little animation that you can find under Mastering Astronomy. And the way this works is I can go ahead and on the slider I can change the temperature. So this right now is 2,240 Kelvin. Okay, I'm going to go ahead and decrease the temperature. Oh, sorry, I am increasing the temperature. Darn it. I'm going to go ahead and increase the temperature, and you can see what happens to the curve. It goes up, you know, the intensity increases all around, and its lambda max, which would be about right here right now, slides over to the shorter wavelength. Now let me go ahead and cool it down. 50 Kelvin is what this says over here, and this would be like the radiation curve of an object that is looks like 75 Kelvin. So notice that it's diminished in its intensity, and notice that the peak has moved over here to longer wavelength.